Whenever there is chemical combination or reaction, electrons are either lost or gained. And the lost or gain of electron usually occur at the outermost shell. The number of electron loss or gain is known as the valence of that element. Generally, metals lose electrons, while non-metals gain electrons. For example, metals like sodium, the atomic number of sodium is 11. That 11 represents the number of protons because atom in an atom of an element. And note that number of protons is always equal to number of electrons in a neutral atom. Therefore, the number of electrons is also 11. Now, these electrons are arranged in a cloud-like manner around the nucleus. There is a revolve around the nucleus in a cloud-like, and the path through which they revolve is called the shells of. So the outermost shell of sodium has one electron. So whenever sodium undergoes combination with other atoms, this outermost shell electron is lost, and that amount that is lost is known as the valency of sodium. So let's write the configuration. Sodium has 11 electrons. The 2 electrons in the innermost shell, then the next shell to the innermost shell has 8 electrons. Right, the 8 electrons, while the outermost shell has 1 electron. So whenever sodium undergoes combination with other atoms, usually this outermost shell electron is so that when that electron is removed, sodium becomes a charged particle, which is indicated by this plus here to show that sodium is now having excess of positive charge. Recall that electrons are negatively charged, while protons are positively. So for a neutral atom, where the number of electrons and the number of protons are equal, the charges will cancel out. But the moment sodium lost 1 electron, then there's no more equal charges, positive and negative. By removing 1 electron, the number of protons is more than the number of electrons. What is indicated with this that the sodium is having excess of proton. This charged sodium, whenever it comes in contact with another atom that is negatively charged, there will be an attraction between the two of them because unlike charges will always attract. Recall that sodium is losing 1 electron. When you lose that electron to become sodium, the electron that is lost, something must collect that electron. Sodium cannot just randomly give out the electron. There must be a non-metal that is available to receive this electron. And so if you have a non-metal like chlorine, chlorine can accept that electron from sodium. So that as chlorine becomes a chloride ion that is having more of negative charges. That is what we denote with this negative or minus. But I can say that like charges will always attract themselves. So this positively charged sodium ion will attract this negatively charged chloride ion to form a bond, a type of bond known as electrovalent bond or ionic bond. And so because this attraction occurs as a result of loss of electron and gain of electron by sodium and chlorine respectively, then we can also define valency as a combining power of elements. And because whenever there is a combination between atoms, it happens as a result of this valence element. Either the electron is lost or usually metals will lose electron, while non-metals will gain electron. We can therefore define valency as also the combining power of an element. Even when there is a covalent bond still occur between these valence electrons, as the outermost shell electron. Therefore, defining valency as the combining power of elements is also correct in that regard. The valency in summary is division or the combining power of an element. Usually, metals will lose electron, while non-metals will gain electron. Now, elements have a valency of +1, other have a valency of +2, other have a valency of +3, depending on the number of electrons in the outermost shell. So sodium here, for example, has 1 electron in the outermost shell. So whenever it undergoes combination, it is this 1 electron that will be removed. So the valency of sodium is +1. Now for an element like magnesium that has 2 electrons in the outer shell, so if I am to write the configuration of a magnesium, I just need to add 1 electron to it, with this sodium here, and it becomes 12 electrons altogether for the configuration of magnesium. So if magnesium combined with other atoms, these 2 valence electrons are usually removed. That is, for a magnesium atom to become an ion, these 2 electrons are removed. So that when that happens, then you have magnesium ion plus the electron that's the 2e minus. So the valency of magnesium 2, it has two valence electrons that are involved in chemical combination. And for an element like aluminium that has 3 in the outer shell, the atomic number of aluminum is 13. So if you write the configuration here, that means I will need to add one more electron there. And so that whenever aluminum combines with other atoms, these outer electrons are usually the one involved. They are removed, then non-metal accept the three of them. So these three outer electrons makes aluminum to have what? Valency of plus 3. That is, whenever it ionizes, these three electrons are removed. That is 3 plus and plus the electrons that are removed. Now, apart from having this single valency, there are some elements that have variable valency. That is, they can have more than one valency. A good example is iron. Iron is a variable oxidation or variable valency. For example, it can have iron 2, which is plus 2. The valency is plus 2. And also have iron 3. The valency is plus 3. That's in short, there's iron 1, but it's not stable. So it doesn't exist in nature. That's why we consider only iron 2 and iron 3. The point here is the valency of metals are usually plus, while that of non-metal are minor, because metals lose electron to become positively charged, while non-metals accept electron to become negatively charged. So when writing the valency of metals, we use a positive sign, but the valency of non-metals we use a negative sign. And their oxidation number, some of them have more than one valency, while some other one have just one. So the first one here, aluminium, is 3. That's 3 electrons in the outer shell. Then argon. Argon has no valency. Like it has no oxidation number. Why is it so? All the noble gas elements, they don't have oxidation number because they don't react. Their outer shell is completely filled. Before atoms can react or before atoms can combine, the outer shell needs electron or needs to give out electron. So anything outside 2 electron or 8 electron in the outer shell means the atom is unstable. What do I mean? For element like helium that has only one shell, helium has only one shell, and this one shell accommodates a maximum of 2 electrons. If it can accommodate a maximum of 2 electrons, and helium has 2 electrons, that means the shell is completely filled. As such, helium does not need to give out any electron and it does not need to accept any electron. Now, atoms give out electron or receive electron if they are unstable. And then what makes them unstable is this outer shell. If the outer shell is not filled, that atom, that element will be unstable. So for helium, it is completely filled because this shell, this one shell that it has, can accommodate a maximum of 2 electrons, and it already has the 2 electrons. As such, helium is inert, that is unreactive. That's the meaning of inert. Because all the group 8 elements. For other group 8 elements, they have 8 electrons in their outer shell. Remember, the configuration of stability is having either 2 electrons in the outer shell or 8 electrons in the outer shell. Now, helium here too, because that is the only one shell it has. This shell can accommodate argon, for example. Argon is what is the atomic number of argon? 13 of it. Let's see. That's 2, 8. That's it. Let's write the configuration. The inner shell can accommodate a maximum of, the next shell can accommodate a maximum of 8. Then the outer shell can also accommodate a maximum of 8. So this shell can accommodate a maximum of 8, and it already has that 8. That means this atom is stable. It doesn't need to combine. It doesn't need to react with anything. Atoms react because they are unstable. And what makes them unstable is either they need more electrons in the outer shell or they have less than required number of electrons in the outer shell. So for example, metals that have between 1 electron to 3 electrons in their outer shell, these 1 or 2 or 3 electrons in their outer shell make them unstable. So they prefer to give out those electrons in the outer shell to achieve stability. And they do that by reacting with other atoms. That is what bring about chemical reaction. Atoms are unstable if they have one electron, two electron, or three electron in their outer shell. To get seven extra, for example, sodium that has one electron in the outer shell, to get seven extra electrons to become stable is not easy. There's no atom or there's no element that will be willing to give out seven electrons to sodium. So sodium prefer to give out this one electron and become positively charged sodium. Then for element like chlorine that has seven electrons in the outer shell, because you need eight electrons, you already have seven. Doesn't make sense to give out that seven. Rather, you look for some one air that is willing to give out one, collect that one from the person. And that's why there's usually a reaction between sodium and chlorine. Because chlorine has seven electrons in the outer shell. You need one extra electron to achieve stability. And sodium has one. You need seven to achieve stability. It's not easy to get seven. They prefer to give out the one to chlorine. Chlorine accepts it, and then a bond is formed between sodium and chlorine, ionic bond in that case, which is due to attraction between positively charged sodium and negatively charged chloride ion. So this is chlorine atomic configuration. It has seven electrons. 1, 2, 3, 4, 5, 6, 7. To get one electron is very easy. You get that electron from anyone that is willing to donate. Unlike sodium that has one electron in the outer shell, to get seven extra, it's not easy. Also, that applies to atoms that have two electrons in the outer shell. They need six more electrons. To get six is not easy, so they prefer to give out the two. The same thing applies to atoms that have three electrons in the outer shell. They need extra five to achieve stability. To give five is not easy, so they prefer to give out the three. That is why metals react by losing their outer electrons, since they usually have between 1 to 3 electrons in their outer shell. To get extra 7, 6, or 5 is not easy. So they give out the outer electron to become positively charged ion. Why non-metal have between 4, 5, and 6 electrons in their outer shells? And so they can easily accept electrons from metals and become negatively charged ions. And the noble gases, the group 8, that have 8 electrons in their outer shell, with the exception of helium that has only 2. They don't react at all because their outer shell is completely filled. So they are stable. They don't have any valency because they don't react. Okay, so argon, the valency is nil. It doesn't react because the outer shell is completely filled. And barium, the valency is 2. It has 2 electrons in the outer shell. Then bromine, the valency is 1. Calcium, the valency is 2. Carbon, it has variable oxidation number plus 2 to be 4, either 2 or 4 for carbon. Then chlorine is 1, copper is 1 or 2, gold is 1, helium is nil. It doesn't have because it's a noble gas. The outer shell is filled. It has only one shell actually, and that one shell can accommodate only 2 electrons. Helium as an atom has 2 electrons, so those 2 electrons are just filled the shell that it has. Then hydrogen, the valency is 1. Hydrogen has only 1 electron. Then iodine, the valency is 1. Then iron, the valency is 2 or 3, variable oxidation. Then krypton. Krypton is also a noble gas, a group 8 element, so the valency is nil. Then you have lead, which has variable valency, 2 or 4. Then magnesium, 2. Mercury also variable, either 1 or 2. Then neon is also a noble gas. It doesn't react, it's inert. Then nitrogen is 3 or 5, variable. Then oxygen, the valency is 2. Oxygen has 6 electrons in the outer shell, so it needs 2 extra electrons to fill the outer shell. So it accepts the 2 electrons from metals. Then phosphorus has variable valency, either 3 or 5. Potassium is 1. Potassium is 19. That is 2881. That is potassium configuration 2881. Then what is it called? Silver is 1. Sodium is 1. Sulfur is 2, 4, or 6. That is variable. Then zinc is 2. So that is that for valency. In summary, it is what? The number of electrons lost or gained during chemical combination, or the combining power of an element or a radical. Now, what are radicals in the first place? Radicals usually are a group of atoms that behave as a single unit. In other words, whenever they undergo reaction, even though they are different atoms, but they react as one single entity. A good example is triisonitrate 5, triisonitrate 5, tetraisosulfate 6. All of these are radicals. Whenever they react, they behave as a single unit, even though you have several atoms there. Like this now, these are 4 atoms, 1 of hydrogen and 3 of oxygen. Here, 5 atoms, 1 of sulfur and 4 of oxygen. But whenever they react, this is like this is going to act as a single unit. This is going to act as a single unit. So group of atoms that behave as a single unit like this are called radicals. And the radical may be charged and have oxidation numbers, which are usually represented by the net number of positive or negative charges they carry. For example, when I write this NO3, I indicate a number on top of it. This number is the oxidation number. So NO3, I wrote together, is supposed to be NO2, 3 to the power of negative 1. Then SO4 to the power of negative 2. So this is oxidation number. Oxidation number. The table below shows some common radicals and their valency. Ammonium. Ammonium is NH4, that is the formula for ammonium. Then hydroxide is OH minus. Triisonitrate 5 is NO3 minus. Diisonitrate 5, NO2 minus. Then triisocarbonate 4, CO3, 2 minus. And then hydrogen triisocarbonate 4, that's HCO3 minus. Tetraisophosphates 6, that is SO4, 2 minus. Okay, so the valency is this charge indicated. That is why this is plus 1. So the valency is 1. This is negative 1. The valency is 1. This is negative 1. Also, the valency is 1. Negative 1, the valency is 1. Negative 2, the valency is 2. Negative 1, the valency is 1. Then negative 2, the valency is 2. So in essence here, the valency is the numerical value without the charge, while oxidation number is the numerical value plus the charge, either the positive or the negative charge. Now, there are exceptions to everything. The oxidation number of hydrogen in most compounds is usually plus 1. That is hydrogen, because it has only 1 electron. This 1 electron, depending on the condition of reaction, sometimes hydrogen may give out the 1 electron. Some other time it may accept 1 electron. In most compounds, it gives out the 1 electron to become hydrogen plus, except in metallic hydrides, where it is usually negative 1, that it accepts electron in metallic hydride. So that is an exception. In most compounds, the oxidation number of hydrogen is plus 1, with the exception of metallic hydrides, where it is negative 1. Also, the same thing happens to oxygen. In most compounds, the oxidation number of oxygen is negative 2, with the exception of peroxide, where it is negative 1. Now, what is the essence of learning this valency? The oxidation number. Because I will define valency as a combining power of element also. Now, why do we define it as a combining power? For you to be able to write the formula of a compound, you should first of all know the component atoms and component radicals. Then you should also know the oxidation or the valency of each of the component atom and radical before you can write the formula of any compound at all. Those two things must be known. The component element, their valency. So the formula of a compound can be deduced from the valency of the component element or radicals. The valency helps us in constructing the formula of compounds. The following rules apply in writing the chemical formula of a compound. First of all, write the symbol for the element and of the symbols. Rewrite the symbols by exchanging the valency of the component element and write the numbers below to the right of the symbol. And the sum of positive valencies of a compound must equal to the sum of its negative valency. And also the number of atoms of the component elements in a formula must be written as a numerical subscript after the element concerned. If a radical occurs more than once, it must be enclosed in parentheses. So for example, consider a hypothetical compound consisting of 2 elements A and B. Now the valency of A, let it be X. The valency of B, let it be Y. So these are the component elements of a hypothetical compound. This is a hypothetical compound consisting of A and B as the component element. Now the valency of A is X, the valency of B is Y. For us to write the chemical formula of that element, we need to exchange the valency. As B is going to take the X, YA is going to take the Y. As there's an exchange of valency. And that is why we say valency is combining power of elements. So that the formula of that compound will be AY and BX. There is an exchange of valency. This A take the valency of B, YP take the valency of A to give us the chemical formula of that compound. We have some example here. So using the example above, write the formula of the following compound. Sodium hydroxide. So like we said, first of all, we need to know the component, element, and radical. Sodium hydroxide has sodium as one of the component elements. Then hydroxide is the radical. Of course, they give us a table here of which hydroxide is one of the radical. Look at it here. And the formula is OH minus. I mean, the valence is 1. The valency of sodium is +1. The valency of hydroxide is -1. So for a bond to be formed between them, for a reaction to occur between them, there has to be an exchange of valency. So hydroxide will pick the 1, sodium will also pick the 1. Both of them are 1, 1. Then the formula of sodium hydroxide is NaOH. When it is 1, we don't need to write it. We don't need to write 1A, 1A. Is the formula of sodium hydroxide. And the next one is calcium oxide. Calcium, Ca, as component element, calcium oxide, then oxygen, that's oxide. And the valency of calcium is that of oxygen is also for the compound to be formed. These elements will exchange their valency. So oxygen will pick the 2 from calcium. Calcium will also pick the -2 from oxygen. So that the formula is Ca2O, but 2 can cancel out and they are the same. So that the formula is Ca, as we divide the 2 because the fact that they are the same. When the numbers are the same, you can divide them. So that the formula is Ca, that is calcium oxide. The next one is water. Water is hydrogen and oxygen. The hydrogen, the valency is 1. Oxygen, the valency is 2. So for a compound to be formed, they have to exchange their valency. Oxygen will pick 1, and nitrogen will pick the 2 from oxygen. So we have H2, that is this 2 here, this is it here. That is exchange of valency. And the next one is, ammonia. Ammonia is nitrogen. Now recall that nitrogen has variable oxidation state. So in ammonia is N3, then hydrogen is 1. So that is supposed to be minus. Nitrogen is non-metal. Then by the time they exchange their valency, hydrogen will pick 3 from nitrogen, while nitrogen will pick 1 from hydrogen. So that the formula becomes NaH. And the next one is calcium hydroxide. Calcium, the valency is 2, while hydroxide is a radical, and the valency is -1. So that when there is a combination between calcium and hydroxide, hydroxide will pick the 2 from calcium, while calcium pick the 1 from hydroxide. So that the chemical formula is Ca, and because these two affect a group, that is 2 atoms, hydrogen and oxygen, then we're going to enclose this OH in a parenthesis. Understand? So the chemical formula for calcium hydroxide is CaOH, then brackets 2. These two affect this group, this hydroxide group. And the next one, white chloride, valence is also 1. When they combine, sodium and chlorine will exchange valence. So that formula is NaCl, because both of them are 1, 1. When it is 1, we don't need to write it. And the next one is sodium oxide. Sodium, the valence is 1. Oxygen, the valency is 2. So when there's a combination, there's an exchange of valency. The sodium will pick 2 from oxygen, while oxygen pick 1 from sodium. So the chemical. And the next one is calcium chloride. Calcium is 2, that's a valency. Chloride, when there's combination, there's an exchange of valency. This chlorine will pick 2 from calcium, so that the formula is CaCl2. Aluminum chloride, aluminum, the will 1. When there's combination, this chlorine will pick the 3 from sodium, from aluminum. While aluminum will pick the 1 from chlorine. The 3 is coming from aluminum. There's an exchange of valency there. And the next one is aluminum oxide. aluminium oxide. Again, aluminium is 3, oxygen is 2. So when there is a combination between the two of them, oxygen picks 3 from aluminium, while aluminium picks 2 from 2O3 as aluminium oxide. The next one is aluminium nitride. They either have valency of 3 or 5. The aluminium nitride, for aluminium nitride, nitrogen with a valency of 3. You have nitrogen, the nitrogen is 3. So when there's a combination, there's exchange of valency, and so that aluminum nitride is Al. And then the next one is ammonium hydroxide 4 plus. And hydroxide is also a radical OH minus. So when there's a reaction, a combination between the two of them, ammonium, 1 from hydroxide. So the formula is NH4OH is 1 without it. And the next one is tetrazosulfate 6. And tetrazosulfate 6 is SO4 2 minus. So when they react, they exchange their valency. Ammonium pick 1 from ammonium. So that the formula is NH, but there is a 2 coming from sulfate. So we need to enclose this NH4 in a parenthesis. So NH4 2 and SO4. And the next one is ammonium tetrazophosphate 5. So NH4 ammonium. Then tetrazophosphate 5 is PO4. PO4. That's tetra for 4. Oxygen for oxygen and phosphate 5. That's PO5. And tetrazophosphate 5, the oxidation number is at the time they combine together, there's an exchange of valence. So that ammonium will take this 3 from tetrazophosphate 5, while tetrazophosphate 5 will take 1 from ammonium. So that the formula is NH3, NH4 rather. And this 3 that is coming from phosphate, they affect this group. So we enclose this group, that is ammonium, in a parenthesis. Phosphate, that is ammonium tetrazophosphate 5. And the next one is copper 2 hydroxide. Copper 2, because copper exists as a variable oxidation state. So it is indicated here that it is copper 2. It could be copper 1, it could be copper 2. So copper 2, I see, then 2 plus is copper 2. A hydroxide, radical section number is 1, you get to 1. So when there's a reaction, hydroxide picks 2 from copper, and copper picks 1 from hydroxide. So the formula is C. And this 2 that is coming from copper is going to affect this group, this hydroxide group. So we need to enclose this hydroxide group in a parenthesis. So that's copper 2 hydroxide. The next one is copper 2 tetrazosulfate 6. And copper, the oxidation number there is 2, it's indicated copper 2. And tetrazosulfate 6, again the oxidation number is -2. So when there is a combination, they exchange their valency. The sulfate pick 2 from copper, and copper also pick 2 from sulfate, so that the formula is Cu. When they are the same, 2, 2, we don't need to write it. The CuSO4, but the 2 are going to cancel out. Then the next one is copper 2 tetrazophosphate 5. Copper 2 tetrazophosphate 5. And copper 2 is Cu, and 2 plus tetrazophosphate 5. The oxidation number is 3. So when there's a reaction, copper will pick this 3 from phosphate. Phosphate will pick these 2 from copper. So that the formula becomes Cu3, the 3 that is coming from phosphate. Then PO4, PO4 in a parenthesis. The next one is iron 3 hydroxide. Iron 3, it is indicated already that the oxidation number there is 3. So iron 3, we write that as Fe3 plus. And hydroxide, the oxidation number is -1. When there is a reaction between the two, they exchange their valency. Hydroxide picks 3 from iron, and iron picks 1 from hydroxide. So the formula becomes Fe. Now this 3 that is coming from iron affect the whole of this hydroxide group. So we are going to enclose the hydroxide group in parentheses. So okay. Then the last one, iron 3 tetrazosulfate 6. That's Fe3 plus, and tetrazosulfate 6 is SO4 2 minus. When there's a reaction, there's exchange of valence. Sulfate will pick these 3 from iron. Then iron will Fe2, the 2 that is coming from sulfate. Then this 3 that is coming from iron affect the whole of sulfate group. So we're going to enclose the sulfate in a parenthesis. So SO4 times 3, and 3 from iron. So that is how to write the chemical formula of a compound. First of all, we need to know the component element or the component radical and their respective valency. Whenever there is a combination, there is usually an exchange of valency between the component element or component radical.